Welcome to this lecture of differential calculus. In this lecture, we shall study about the singular pointers. We begin this lecture with the definition of a singular point. So this is a singular point. This is defined as a point, say x naught, y naught on a curve f of xy equal to 0 is said to be a singular point if the derivative of f with respect to x is equal to 0 and partial derivative of f with respect to y is also equal to 0 at this point x naught comma y naught. So therefore a point on a curve where both the partial derivatives become 0, we call that point as a singular point. Now before taking any examples, we shall first classify some different kinds of singular pointers. So this is the classification of singular pointers. First we define one notation here. So let's take up this notation. This notation is denoted by delta, and this is defined as a quantity del square f by del x square y whole square minus del square f by del x square into del square f by del y square. So if we are given a curve f of x y equal to 0, then we evaluate the second order partial derivatives and define this delta as this quantity. Now the first point that we want to note here is that if this delta is greater than 0, suppose at any point x naught y naught, then we say x naught y naught is a node. So therefore a singular point at which this delta becomes positive, we call that singular point as a node of the curve. And node is defined as, so this is in particular a point. So this is a point at which the curve has two distinct real tangents. So therefore a point on a curve at which the curve has two distinct real tangents, we call that point a node, and it is classified by using the concept of singular pointers and evaluating this delta. And if this delta happens to be positive at a singular point, then that is a point which is a node at which the curve will have two distinct real tangents. Now the second value that this delta could have, if delta is equal to 0, then the point x naught y naught is called a cusp, and this is defined as a point. This is the point on the curve at which the curve has coincident real tangents, at which the curve has two coincident real tangents. So that means we will have two tangents at a point, but they will look like a single straight line. And similarly, we have a third classification. If this delta is less than 0 at some point x naught y naught, which is a singular point, then this singular point x naught y naught is called a conjugate point. This is a point at which, or it is also known as isolated point, and at this point the curve has imaginary tangents. And we shall also mention here this conjugate point is also known as an isolated point. So therefore we have taken three classifications of singular pointers depending on this notation delta, which is defined in this way. Now this will be a real number. If this delta is a positive real number, then we call that particular point as a node. If this delta is 0, then we call that singular point as a cusp, and if this delta is negative, then we call that particular singular point as an isolated point or a conjugate point. Now again, before going into the examples, we shall take some pictures here, and we will try to understand these types using graphs. So here, let's consider a graph of this shape. So suppose if we have a curve that looks like this, then this is the point which will be a singular point. So we will have this point P. Let's denote it by P of x naught, y naught. Then it will have the tangents like this. So then we can draw one tangent on this branch like this, and we can also draw another tangent on the same point like this. So therefore this is a point at which this curve has two real distinct tangents. So when it has two distinct real tangents at this point, so graphically we can say that this point is a node. Now similarly, the second graph that we shall take here is like this. So again, if we look at this point, we can call this point as, suppose again, P with coordinates x naught, y naught. Then we can draw a tangent on these two points of the curve like this. So this is the tangent, and this curve has actually two branches. This is, suppose, branch 1, and this is branch 2. Now this tangent T, this is tangent to branch 1 at point P, and this is also a tangent to branch 2 at point P. So that means this T is actually, these are two tangents to these two branches, but they are coincident with real tangents. So therefore we can call this point is a cusp. Now suppose we have any of these two curves, and we find out a singular point which suppose lies here. Suppose this is a point Q with coordinates, suppose x1 comma y1. Now as this point does not lie on this curve, and this happens to be one of the singular points, and this is in fact obtained by solving the equations del f by del x equal to 0 and del f by del y equal to 0, then this point, as it does not lie on this curve, so whatever the lines that pass through this curve, they will not touch this graph at this point. So therefore we can just think of there are imaginary tangents to this graph at this point Q. So therefore we can say that this point is an isolated point or a conjugate point. So therefore this is a conjugate point, and in fact its better name is an isolated point. Now let's move towards taking some examples. Here we take one example where we will classify and also find out the singular points and then classify them as nodes or cusps or a conjugate point. So this is our example. We want to find out and classify the singular points of these two curves. Now let's take up the solution of the first one. So first of all, we are given y square is equal to x square into x plus 1, which we can also write as x cube plus x square. Now first of all, let's find out the partial derivatives of this function with respect to x and y, and then equate them to 0 to find out the singular points. So then this del f by del x, or we can define like this, or we have this f of xy is equal to y square minus x cube minus x square is equal to 0. So therefore del f by del x, this is equal to, now we have to take the partial derivative with respect to x, that becomes minus 3x square minus 2x. And similarly the partial derivative with respect to y, that is del f by del y, this is equal to just 2y. Now equating both of them to 0, so now this is equal to 0 and this is equal to 0. Now from here we obtain x is equal to 0 and x is equal to minus 2 by 3. And similarly from this equation we just obtain y is equal to 0. Therefore the singular points are, now it will be an ordered pair made using the value of x and the value of y. So it is like x is equal to 0, y is equal to 0, and the second point is x equal to minus 2 by 3, y is equal to 0. Now first of all we want to understand whether these 2 points lie on the curve or not. Now if we substitute x equal to 0, 0 in the given curve y square equal to x square into x plus 1, we obtain the point 0, 0 satisfies this curve. But if we substitute x equal to minus 2 by 3 here in this curve and y equal to 0 here in this curve, we will get some 0 is equal to a non-zero value. And in fact, we can see that this point does not lie on the curve. So we can say this minus 2 by 3, 0 is a conjugate point, and 0, 0 is either will be a node or a cusp. So first of all, we check which of these points lie on f of xy is equal to y square minus x cube minus x square is equal to 0. So then what we do, first of all we substitute the point 0, 0. So this gives us f of 0, 0. This is equal to 0 minus 0 minus 0, and this in fact equal to 0. And for the second point, when we substitute minus 2 by 3 comma 0, then we obtain f of minus 2 by 3 comma 0, and this gives now y is equal to 0, and we get x is equal to minus 2 by 3 whole cube, then minus 2 by 3 whole square. Now if we equate this to 0, so this implies us some non-zero quantity is equal to 0. In fact, this minus 2 by 3 whole cube minus 2 by 3 whole square, this will be a non-zero quantity, and this equated to 0 gives us some non-zero value equal to 0. That means this point minus 2 by 3 comma 0 does not lie on the curve. So this implies minus 2 by 3 0 does not lie on the curve. So this implies minus 2 by 3 comma 0 is an isolated point. Now let's try to evaluate what kind of singular point is the point 0. So the next we evaluate this del square f by del x square, which is equal to, now we already have del f by del x. Del f by del x was evaluated to be equal to minus 3x square minus 2x, so its derivative now again will be equal to minus 6x minus 2. So this is minus 6x minus 2. And similarly, del square f by del y square, this will be equal to 2, and del square f by del x del y. Now here we have two ways to evaluate del square f by del x del y. Either we differentiate this del f by del x with respect to y, or we differentiate del f by del y with respect to x. And if we look into these things, if we differentiate del f by del x with respect to y, we will get 0. If we differentiate del f by del y with respect to x, we will again get 0. So therefore, this is equal to 0. So hence, our quantity that was defined to be equal to delta, and this was defined as del square f by del x del y whole square, then minus del square f by del x square into del square f by del y square. Now this is equal to 0 minus, add the point 0, 0. So first of all, this is equal to 0 minus 6x minus 2 into 2. So therefore this is equal to 2 into 6x plus 2. Now at 0, 0, hence at 0, 0, hence this quantity delta at 0, 0 gives delta is equal to 4, which is greater than 0. Now when we have delta greater than 0 at a singular point, we know that singular point is called a node. So therefore this point 0, 0 is a node. So this is how we classify singular pointers. Now on similar lines, we can evaluate the second part, y square equal to x cube. We have to take its partial derivative with respect to x and y. Then we will obtain a singular point. Then we have to classify that singular point by just evaluating this delta defined in this way and see if this delta becomes positive or negative or 0.